Hi everyone. In this video we are going to start chapter 9 in the third edition of the Klein textbook, or chapter 10 if you have the second edition of the Klein textbook. So we're covering the chapter on alkynes and different reactions that we can do with alkynes. So off to the left you can see a reaction map that's similar to the one we saw for the previous chapter. And you'll notice that we can start with an alkyne. And this one in particular has an alkyl group on one side and then a hydrogen on the other side. Now we could take that alkyne and we could add another R group. Or we could take that original alkyne and add some halogens. We could just turn that into a carbonyl, so a ketone, or an aldehyde. We could also, let's see, down below, we could turn this into a double bond or a single bond. We could also try to make sure we have just the cis alkene or the trans alkene, depending on what we're trying to achieve. So there's all sorts of different reactions we can do to get a desired product if we start with an alkyne. So they're pretty useful. All right, now before we actually dive into alkyne reactions and their mechanisms, I do encourage you to review the following topics if you're feeling a little rusty, especially if it's been a while since you've taken organic chemistry. So the first topic is Bronsted-Lowry acidity, and that's covered in chapter 3 of either Klein textbook, the second or the third edition. I also encourage you to make sure you understand nucleophiles and electrophiles, as well as energy diagrams and arrow pushing mechanisms. And all of that can be found in chapter 6. All right. Now, in this video, we're just going to review what we already know about alkynes because we have talked about triple bonds previously. And then in the next video, we'll start diving into some reactions and mechanisms. So let's start by reviewing the structure of a triple bond or an alkyne. All right, so let's say we have the molecule acetylene, which is the simplest molecule with a triple bond here. Okay, and let's first look at an orbital diagram for one of these carbons. So let's just focus on the carbon on the left. And let's draw its orbital diagram, so its energy diagram. All right, so we know that carbon has how many total electrons? 6. Okay, and we know that the lowest energy orbital is the 1s orbital, and then that's followed by the 2s orbital, and then that's followed by 3 2p orbitals. All right, so if there are 6 electrons in a carbon atom, the first 2 will go into the 1s orbital, the next 2 will go into the 2s orbital, and then we have 2 unpaired electrons in the 2p orbitals. Okay, now this doesn't really explain how carbon is bonding here. So instead of using this particular orbital diagram, so the atomic orbital diagram, we're going to hybridize our orbitals. So what we can do is first we want to figure out what is the hybridization of our carbon in the acetylene molecule. So is it sp hybridized, sp2 hybridized, or sp3 hybridized? So it's only bonded to 2 other atoms, and if it only has 2 bonds, its steric number is 2, which means that its hybridization is sp. Okay, so what that means is we're going to hybridize the 2s orbital and one of the 2p orbitals. So we have one s and one p combining together. And then we'll have 2 unpaired p orbitals left over. All right. Now, we're really just focusing on the valence electrons here. The inner electrons in the 1s orbital, they just stay there. They don't really get touched. So we'll just leave that the same. But once we combine the s and p orbitals up above, that's going to give us new orbitals, new hybrid orbitals called sp orbitals. And again, we have our leftover 2p orbitals above that. All right, so now when we're filling out our hybridized orbital diagram, we still have 2 electrons in the 1s orbital. Those don't get touched. And now we're going to place 1 single electron in each of our other orbitals. So they're all equally spaced out. Okay, so what would that look like if we were to draw these orbitals? So let's just draw that carbon that I highlighted. And sp orbitals, remember, are really short because they're 50% s, and s orbitals are spherical, right? So these are pretty round. They're fairly short, something like that. And then there's those 2p orbitals. I'll draw those in a different color. So one of those 2p orbitals will probably be up and down, and the other one will be 90 degrees off from that one. So it's kind of going back and forward. So I'll just fill those in. Okay, so carbon can now make bonds using its sp orbitals, which are in black. And if we look at our acetylene molecule up above, the carbon on the right-hand side also is sp hybridized. So we can draw that one as looking very similar to our carbon on the right. And this one will also have p orbitals 90 degrees from each other. Okay, now remember, if we look at our hybridized energy orbital diagram, we have 1 electron in each of the sp orbitals. So if we focus on the carbon on the left, it has an electron on the sp orbital on the left, and it also has an electron in the sp orbital to the right. Similarly, it has an electron in one of its p orbitals and an electron in its other p orbital as well. I'll draw that in black to make sure it stands out. And same thing for the other carbon on the right. That has an unpaired electron on the right-hand side and in the left-hand sp orbital. So now we have a set of paired electrons in the middle. and that will be our sigma bond. Okay, and then it also has an unpaired electron in its one of its p orbitals as well as the other one. Okay, so now we can actually start pairing up those p orbitals, and they're going to make pi bonds. So we kind of get this spread of electron density across the top, the bottom, and then the back and the front. So even though I drew those electrons as being statically placed, so they're staying still, they're actually moving around. So there's an equal likelihood that they're on the top or on the bottom. So we get that kind of top and bottom electron density, or back and front. So those are our pi bonds. Okay, so again, remember a triple bond is made up of one sigma bond and two pi bonds. Now the last thing we need to show are the hydrogen atoms on either side of the molecule. And remember, hydrogen atoms are the simplest atoms. They are going to just have one electron in a 1s orbital. And those will just be spherical, so we can just draw a sphere. And that one electron with hydrogen is going to pair up with the unpaired electron in carbon's sp orbital. So those are also sigma bonds off to the side. All right. So I hope that helps refresh your memory a little bit on the structure of triple bonds and kind of what they look like three-dimensionally. Now, if this is at all confusing, or if you don't remember this, I think you can go back to chapter 1 and review some of that content. Or if you have questions about it, just ask me. I'm pretty available. All right, so let's look at nomenclature for triple bonds. So how do we name alkynes? So the first thing we want to do is name the parent chain. So we want to identify and name parent chain. And you want to make sure that the parent chain includes the triple bond. Then you're going to identify and name any substituents. Then you're going to number the parent chain and assign a number to each substituent. Now, when you number the parent chain, you want to make sure the alkyne has the lowest number possible. All right, and then finally, when you're writing out the full name of the molecule, you want to make sure to list the substituents alphabetically. Okay. So let's go over an example. So let's say we have the following alkyne. Okay, and I want you to try to name this alkyne yourself first, and then we will go over it together. So you can pause the video and try to name it, and when you unpause, we'll go over it. Okay, so again, we want to first identify and name the parent chain. So I'm just going to highlight the longest chain that contains the alkyne. Okay, so I'm going to start from the left. So that at least includes the alkyne. All right, and then the next carbon. Now here we have a few different directions we could go. We could go downward to those methyl carbons, or we could go up to the right. And it looks like if we go up to the right, that will include more carbons, so we want to do that. And then we could go either direction here. We could go up or down, it doesn't really matter, they're the same. So I'll just go up. Okay, so that is our parent chain. And let's number, number 2, let's identify and name any substituents. So it looks like we have a substituent on the end here, and then 2 substituents kind of in the middle. And what would we call those substituents? Methyl groups. So these are all methyl substituents. Okay, so we don't really have to worry about alphabetizing the substituents here because they're all going to have the same name. But if you had, for instance, an ethyl group and a methyl group, ethyl starts with E, so it would go first when you're listing the substituents, regardless of its number. The numbers can be kind of out of order in the name. You really just want to focus on alphabetizing the substituents. Okay, so let's move on to number 3. Let's number the parent chain, and we want to number it so that the alkyne has the lowest number possible. And then we'll assign a number to each substituent. Okay, so since the alkyne is really close to the left-hand side of our parent chain, I'm going to start on that side because that will probably give me the lowest number for the alkyne. So I'll start with the carbon on the end, that's number 1. And then the carbon at the beginning of the alkyne will be number 2. The carbon at the end of the alkyne will be number 3, 4, 5, 6, and 7. All right, so it looks like we have methyl groups at carbon 5. We have 2 of them. And then we have 1 at carbon 6. So we've got 5, 5, 6. All right, so let's start naming this molecule. So we'll start with our substituents, and remember to include all of the numbers, 5, 5, 6. So even though it seems redundant to list 5 twice, we want to make sure that it's very obvious where the methyl groups are, because if we just listed 5, 6, we don't know where that third methyl goes. Does it go on the 5 or the 6? So you want to be very clear. And then we'll put a dash, and we're going to put a prefix in front of methyl to indicate that we have 3 of them. So that is trimethyl. Okay, and now we need to also list where the triple bond is. Okay, so the triple bond starts at position 2. So I'm going to put -2 dash, And then we have to name our parent chain. So how many carbons do we have? We have 7 in our parent chain. So that is going to give me a prefix of hept. And then we want to indicate that we have a triple bond, not a double bond or a single bond. So we're going to end this in YNE, ine. So this is 5,5,6 trimethyl 2-heptine. Now there is actually another way that you could name this. The substituent part stays the same, but you could put the 2 in the middle of heptine. So you could write trimethyl hept 2-ine. And that also tells you that the triple bond starts at carbon 2. So either one is fine, whichever one you prefer. All right, and I think your textbook does have a couple of other practice problems, some skill builder problems that you can do to try to practice naming alkynes. So if you're feeling a little rusty on naming, I definitely recommend going over the skill builder exercise. All right, so now the last topic we're going to review is acidity. Okay, so you might recall from last quarter that if you have 2 carbons with all single bonds, we would call that ethane, and that has a pKa equal to 50. And remember that the lower the pKa value, the more acidic the molecule. So ethane is not particularly acidic at all. It has a pretty high pKa value. But now let's add a double bond in there. So we got rid of a couple hydrogens and added a double bond. This is ethene, and the pKa of this molecule is 44. So this also is not very acidic, so it doesn't really want to give up a hydrogen. But now let's look at acetylene, which we saw earlier, where we have a triple bond between those carbons. So we got rid of 2 more hydrogens and created a triple bond. And again, we use the more common name for this molecule of acetylene. And its pKa is 25. So it's still not, a particularly strong acid, but it's definitely stronger than ethene and ethane. So this would be the most acidic, acetylene, and ethane is the least acidic. Now, part of the reason for that is acetylene is sp hybridized, as we talked about before, or its 2 carbons are sp hybridized. And if acetylene loses one of its hydrogens, it becomes the acetylide ion. Let's make sure I'm spelling this right. That is not the correct way to spell acetylide. There we go. All right, so the acetylide, however you want to say it, ion. And this is going to be a more stable base than the base that would result from ethene. And that will actually be more stable than the base that would result from ethane. And the main reason for that is the hybridization. So the carbons in ethane are sp3 hybridized. The carbons in ethene are sp2 hybridized. And then we already said the carbons in acetylene are sp hybridized. So again, the acetylide ion is the most stable conjugate base. And that's because the sp orbital is very round compared to the sp2 orbital, and then even more so compared to the sp3 orbital. Because remember, we're increasing the s character as we go across. So in an sp3 carbon, it's 75% p character, 25% s character, and p orbitals are very, very long. So electrons can travel pretty far away from the nucleus. But when we get down to an sp orbital, that's 50% s character. And so the electrons are kind of stuck in more of this spherical shape. So remember, there's electrons there. So they're going to be closer to the nucleus. And if electrons can be closer to the protons in the nucleus, they'll be more stabilized. So we'll just write here electrons closer to nucleus. And that's what causes the stability of the acetylide ion compared to the other conjugate bases. Now, that being said, it does take a pretty strong base to remove the hydrogen off of acetylene. So I'm just going to erase some of the information on the bottom and then kind of draw a reaction here. But of course, you can always rewind the video if you want to take notes or review what I said. All right, so let's say that we do have acetylene and we want to remove one of those hydrogens. Let's see. Okay, so we got some sort of base, and it should be a strong base. So the base comes in, and it grabs that proton, and the proton leaves behind its shared electrons. And again, we need a really strong base in order to do this. So a couple of options that you can use. You can use NH2. So this has a negative charge. Or you can use a hydride ion. And remember, the hydride ion is going to come from some sort of salt. So lithium hydride, sodium hydride, or potassium hydride. And these are all very strong bases. All right, so now that we've kind of reviewed some of the topics about alkynes, in the next video, we're going to start talking about different reactions that we can use to turn an alkyne into something else. We'll also talk about how to prepare alkynes. So how do you create an alkyne from something else? So what if you start with an alkene? How do you get to an alkyne? And then eventually we'll be able to fill out that reaction map that we saw on the very first slide. All right, now Part of the reason that I went over the acidity of alkynes is because this acetylide ion is going to be very important for a lot of these reactions we're going to cover. So keep that in mind as we go forward, and I will see you in the next video.